Hey, welcome back to science. Please watch carefully. If you were here in class, I would carry this over and would hold this over some of your heads. It'd be fun. Probably whoever's in this closest table, whoever at that table is at table 3, would be the unlucky victim, volunteer, I mean. I'd hold it above their head, and I would reassure them that there's no way I would take their hand, my hand, off the bottom of this. Because everybody knows, oh, wait a second. Just in case you think that this is some sort of a trick, I actually in class would swing this all the way around. Not a trick. It's science. And there really was water in there. How does it work? Well, it's the same way this thing did. It's not actually gross. It's actually from a few minutes ago. And these work. And it still is not suction. Have you figured it out yet? I hope so. And now, this. Hey, and welcome back to science. It's probably time to do a really quick review of what we know about particles thus far. Our story so far. Particles move. They move with random motion. And for here, I'm going to be speaking specifically about gas particles, but it really is any fluid particle. Particles collide. They collide with other particles. They collide with the walls. Those collisions with the walls are the ones that are important to us because the strength and number of collisions each second on a given area is what we have called pressure. One other thing that we do know is temperature is related to the speed of particles. It's important to remember these things as we go through with what we're doing today. So we have been tasked with trying to figure out how a straw works and how the heck these things work. And I'm claiming that it does not use the word suction. That word is incredibly misleading because it implies that you can actually pull with particles. But we learned in previous videos that particles can't pull. They can only push. That S word, that dreaded S word, it pains me. It really does pain me. 3 of my favorite YouTubers, the big 3Ds, Destin at Smarter Every Day, Derek at Veritasium, and Dianna, the physics girl, all use the dreaded S word. They are smarter than that. They are better than that. And they propagate this misconception. It really is disappointing to me. My goal is that none of my students will use that word because they understand what really, really works, how the world really works. My goal is that by the end of this video, I have convinced you that these things should be called pressure cups and that all of these things work based on pressure. Start by doing it this way. First, a little bit of experience from that you've had. If we take a look at an eardrum, you all have a couple of these. Inside of your head, here's your canal, here's the outside. The blue line is representing an eardrum. Hopefully all of you, most of you have probably gone swimming in a pool or a lake and swum down a ways. What happens? Man, your ears start to hurt. At least mine do. They kind of hurt. Let's see if we can come up with an explanation for how that works. Well, as you dive down, you've got more water pushing on you. There's more water pressure. Water pressure increases the deeper down you go. So your poor eardrum, when there's higher pressure on the outside than on the inside, your eardrum is going to bow in. This is probably exaggerated. I'm sure it's exaggerated. But when that happens, it hurts. It's not designed to stretch that far. When you go back up to the surface, the pressures equalize and it goes back to the normal condition. Beautiful. Now you say, yeah, okay, but that's not a gas. But wait, have you ever had your eardrums hurt when you're not underwater? Perhaps you were going up or down a hill in a car or on skis rather quickly, or the ones really hard to argue with, you've been in a plane. In other words, you change your elevation one way or the other. Let's say you're going up. So you're either going up a big hill or you are going up in an airplane. What would be happening in that case? Well, as you go higher up, you're actually decreasing your depth in this ocean. You're saying, ocean? We right now are at the bottom of an ocean of air. And as you go higher up in that ocean, pressure decreases. Therefore, it's going to look the opposite from last time. This time, the inside is going to push your eardrum out. Now, it turns out the inside of your eardrum is actually connected in the back of your mouth. It's not always open. It's a tiny, tiny little tube. Fancy name is the eustachian tube. That tube opens when you swallow or when you chew gum. That's why when you fly in a plane, they say, hey, chew on gum, have hard candy or something, so that you can be swallowing often. And when you open that up, you're kind of equalizing it. And guess what? When that thing snaps back, what do you say has just happened? That's right. You say, oh, my eardrums popped. That popping is equalizing the pressure from the inside to the outside. And it works both ways. If going back down, it would be like that last picture where the eardrum bows in. You swallow, you chew, the eardrum snaps back to normal. My first goal is to convince you that air has mass. To do that, I've got a pretty simple little demonstration here. I have to show you something called a check valve. A check valve is something that will let a fluid flow in one direction, but not in the other direction. Simply put, this one will let it go this way. I can blow air through that side, but I cannot blow air through that way because the valve will not let the air go through there. What I'm going to do is hook it up to this container. Put that in here. Before we go any further, I'm going to quickly get a mass. Looks like it's 112.62. Yeah. One 12.62, 112.63. That works for me. Now, let's set that aside. I'm going to hook this on. Now what I have is a vacuum pump, basically. As I hook this into here, I've got two check valves. Both will let air go that way. Neither will let the air come this way. So when I pull on this, air can only come through here. When I push here, it can only go out that way. I have to hold this down a little bit just to get the seal connected. But as I'm doing this, basically I'm evacuating the air from inside of here. And I can already tell I'm not getting as much air, so I know it's working. I'm getting about that much air that I can push out. So I'm going to do this a few more times. Getting very, very little air out now. And you'll note the lid is on there quite well. I'm going to disconnect this. We're back to what we started with. What were we? 112.63. And now, looks like we're at 112. I got to stop breathing on it. 112.40 or 39. Just in case you think that there's a trick going on here, I'm going to open this up and let the air back in. You'll be able to see the mass change. And we are back to our original 112.60. So this is showing that the air in here actually had some mass. Very neat. So now that we know that air has mass, that kind of gives us that idea of how we are living at the bottom of an ocean of air. And it helps with that straw concept. Right now, air is pushing in all directions. But the liquid, the little bit that's left, is horizontal. So the air can only push down on it. Not only where the fluid is, but also where that straw is. However, if I create a vacuum in my mouth, I'm removing the pressure there. There's still pressure acting on this liquid, but we know what direction do fluids flow. They flow from higher pressure to lower pressure. So if the higher pressure is acting here and there's a lower pressure in my mouth, it's going to follow the straw up to the mouth, thus delivering a wonderful smoothie to my mouth. Recipe below. Let me give you another demo, a better demo. Okay, I'm going to give us two different experiments here, both showing us how strong atmospheric air pressure is. You can see the empty spritzer can. I have a tiny, tiny bit of water in there that I am trying to boil. This Erlenmeyer flask, that shape is called an Erlenmeyer flask, got a little bit of water in there that also I'm trying to boil. In both cases, if I get a full rolling boil there, what I'm hoping to do is push all the air outside, out of the bottles, out of the can, out of the bottle. I want that entire space filled just with water vapor. Nothing other than that. Because I can condense that water vapor back down pretty easily. As soon as it touches some liquid water, it's going to lose its energy real quick. It'll condense back down. It'll take up 1/1000th of the volume that it did a moment earlier, which means if I do that, basically I can make a vacuum or very close to a vacuum in both of these containers. I wonder what will happen to them when I create a vacuum inside them. You'll notice pop can, a little bit different material than the glass jar. Let's see what happens. Okay, I think the Erlenmeyer flask is ready first. That probably isn't too big of a surprise because with more surface area, it has better transfer of thermal energy by conduction. Right now, that thermal energy is not raising the temperature of the water anymore. Now it's going into changing it from a liquid into a gas. Wow, it's amazing how all these units kind of tie in with each other. I'm getting close to being convinced that that Erlenmeyer flask is filled with nothing but water, or very close to it. So what I'm going to do is cap it Then I'm going to invert it and set the other end of this very long straw into this blue water. Get my gloves on. Okay, right now this gas is cooling down a little bit. As soon as that water hits it, it's going to cool down rapidly and we will have a vacuum. It's actually more impressive in person. But you can see there was very, very little left. So that little tiny bubble is all the more air that was in this Erlenmeyer flask. The rest was water vapor, so it then came close to being a vacuum. Ow! Bad idea. Bad teacher. Right now that one appears to be boiling as well. Sure, I'm glad aluminum does not have much mass. Okay, so I'm going to take that and flip it into this and watch what happens here. Whoa! Now, mind you, a bunch of water got pushed inside. Oh, that's what an atmosphere of air does to you. That's how much pressure you are under right now. You poor things. And you've been under this pressure your whole entire life. Oh, it's so tough to take. There will be an It's okay to be smart video that kind of goes into why you don't implode like this can. But this kind of gets to the heart of the matter. You're under a lot of pressure, an entire atmosphere of pressure right now. Does anybody happen to know the value of that number? How many PSI is one atmosphere of pressure? Anyone? Table 4? Hey, nicely done. Great suggestion. It is not 1,000 PSI. Table 2. Oh, that's great. It's a little bit more than 5 PSI. And table 5. Oh, 5 times 3. We have very close to 15 PSI. It's 14.7. I'm totally good with rounding this to 15. 15 pounds of force on every square inch of your body. I don't know how big an inchworm is. Every area, every bit that you have has 15 pounds of atmospheric air pressure pushing on it. That's kind of big. So if we come back to here, the forces pushing on this lid don't even need to equalize it. You don't have to have it perfectly filled with water for those that thought you did. Right now, I've got water and a teeny tiny bit of air pushing down on that lid. But remember, those particles of air from this ocean that we're at the bottom of are acting in all directions. And right now, they're acting up on this surface of the lid. So you have 15 pounds on every little square inch acting on that. There's a whole lot more than 1 square inch. Do you think the weight of that water is 15 pounds or more? Not even close. An even more fun one, I think, is this one. This just has a mesh on top. It allows water to go in. And I can pour water out, but if I go all the way upside down, it's a little bit of surface tension as well as that 15 pounds pushing up right there. This is kind of neat. Again, if I give a path for air to get in, then all bets are off. But right now, it's holding that water in. So have you figured out yet what these things should be called? I probably gave it away already, I don't know. I call them, based on how they work, pressure cups. Take a look at the shape that they are. Now when I push them together and I push the air out from in between them, they look like that. These things are literally being pushed together by the atmospheric air pressure. 15 pounds on every single little square inch right there. Doesn't sound like a lot, but I believe this ends up being around 180 pounds pushing these together. That's kind of impressive. Now I'm sure it's not a perfect seal. I'm sure it's not a perfect vacuum inside there. But it is enough that, well, you guys might remember how heavy these tables are. And this is one of the taller tables. Easily picks that thing up. Pressure cups makes a whole lot more sense because it describes how they work. You'll also notice with these that they're actually easy to move sideways, and once I let some air in sideways, it's super easy to lift off. They also don't work very well on porous surfaces. Why not? Oh, because there's a path for the air to get in. Air particles are kind of small. But possibly the best demonstration that I have, if this next one doesn't convince you that these are pressure cups and not the dreaded S-word cups, I don't know how I'm going to be able to convince you. So this thing is an actual vacuum pump. I had the little demonstration vacuum pump. This is one that's much more efficient, much bigger, much faster. When I turn it on, it's pushing air out through that spot, and it's removing it from this side. What I'm going to do is hook it up to this. We are evacuating this entire chamber right now. I actually have a gauge over here. We're not going to be able to make a perfect vacuum. This pump is not that good. But we're down to less than 1/2 of an atmosphere already. And we'll be able to get it down to about 1/4 to 1/3 of 1 atmosphere. That's kind of neat. Again, it's acting like a giant pressure cup. Air is pushing up on that side. Since I've removed most of the air from here, can't get in. I'm going to close this valve. And I have mostly a vacuum inside of this, down to about 1/4 of an atmosphere. If there's any doubt that I've removed air from there, it's actually quite a bit. Listen to what happens when I let that air back in by turning this valve. A lot of air just rushed back in. So now, if these things function using that S word, then it shouldn't matter if they're in a vacuum or not. They're not going to work in a vacuum, is my claim. It's my claim. Let's test it. It's a big claim. Let's test this. Set them right there. I'll probably zoom you in so you can see better. And we'll test it. Okay, I'm zoomed in, I think as close as reasonably possible. And I've moved the vacuum pump as far away as I can get it to try and cut down on the noise. Let me get that started up. Now as it's going, you're seeing something happening to those pressure cups. They don't seem to be quite as flat as they were a moment ago, do they? They seem to be, well, no longer being pushed together as hard as they were. And I'm thinking, oh, there they went. I went to check on the pressure gauge. So they no longer are being pushed together. So if these truly did work using that dreaded S word, it shouldn't matter if they're in a vacuum. But they don't work in a vacuum where there's no pressure. They have to have something pushing them together. They are pressure cups. Let's let that air back in there again. And no, they're not going to magically push themselves back together. Air's rushing all the way in between. This is super easy to lift off now. These things should be called pressure cups. Here, give it a tug. So have I done it? Have I convinced you that air pressure, atmospheric air pressure, is really, really strong? 15 pounds on every square inch of you and of everything. We saw the can get crushed. Have I convinced you that these things should really be called pressure cups? If you were here in class, I'd be able to give these to you and challenge people to be able to pull them apart. It's rare that I find somebody able to. I will even give them to two sets of students, and they can pull, and it's actually kind of rare that they can pull them apart. Scares me a little bit sometimes because when they do come apart, students kind of go flying, and I don't want anybody getting hurt. Have I done my job? Are you convinced that pressure is how straws work? Atmospheric air pressure is how vacuum cleaners work, even though we didn't cover that one. And atmospheric air pressure is how pressure cups are held together. There'll be a couple more professional videos that I'll have set up that will help. There's an OK to Be Smart that does a great job. There's a Veritasium where he uses poor words, but he does a good job of explaining it. We'll have that. And we'll even throw in a Bill Nye for good measure. Hope you've had a good year. I certainly have enjoyed working with you guys. I know this was not the way we wanted to learn for the last part of the year. Looking forward to seeing you again in a few years when things are good. I hope back to normal. Seeing many of you guys in my physics class. See you later. Take care.